In the other class, we have discussed the factors affecting the chemical shift values. We have discussed the electronegativity effect and also the hybridization effect. On the basis of electronegativity effect and hybridization effect, we have discussed the different values of chemical shift observed by different compounds. But now the compounds containing double bonds or pi electrons, on the basis of electronegativity effect and hybridization effect, we cannot explain the observed chemical shift values of compounds containing pi bonds. For example, here the olefinic protons may resonate at 4 to 8 delta chemical shift values, and aromatic protons will resonate at 6 to 9 delta, and for acetylene protons, here the observed chemical shift value is less, or it is shielded, the protons are shielded, but here the carbon atoms is sp hybridized. Carbon atom is sp hybridized. It is expected to be more chemical shift value, but the observed value is less than the expected one. And for aldehyde protons, the aldehyde protons are highly de-shielded. The chemical shift values is more than 9 or about 9 to 10 delta. So these chemical shift values can be explained by the effect that is known as magnetic anisotropic effect. So we will discuss one by one the magnetic anisotropic effects of all these compounds. First one, we will discuss the magnetic anisotropic effect of olefins. Olefins, similar to sigma bonds. In olefins, they contain another bond, that is pi bonds. So pi bonds consisting of pi electrons, they form pi bonds, and these pi bonds in presence of a compounds containing pi electrons or pi bonds, when they are placed in an external magnetic field, they induced and secondary magnetic fields, and this induced magnetic field, this is the direction of the applied magnetic field, and the pi electrons are induced to circulate at right angles to the direction of the applied magnetic field, and they induce secondary magnetic field. And the secondary magnetic field is not uniform in all directions. It is not isotropic. It is anisotropic. So the induced magnetic field is like this. So induced magnetic field is not uniform in all directions, and in the center of the molecule, the induced magnetic field opposes the applied magnetic field. Induced magnetic field opposes the applied magnetic field, and we call it as diamagnetic shielding. And in the periphery, the induced magnetic field is aligned with the applied magnetic field, and we call it as paramagnetic de-shielding. And in the center, we call it as diamagnetic shielding region. Diamagnetic shielding. So here the protons, olefinic protons appears in the paramagnetic zone of the molecule, paramagnetic zone. So therefore this here the induced magnetic field is aligned with the applied magnetic field. So therefore these protons experiences more field along with this one. So these protons are highly de-shielded protons. The chemical shift values for these protons are very much high, and this cannot be explained on the basis of electronegativity effect alone. So the high value of electronegativity, high value of the chemical shift values for olefins can be explained on the basis of magnetic anisotropic. Here the geometry of the molecule determines the position of the protons, and therefore that gives the value of chemical shift. We'll take an example of alpha pinene. We take an example of alpha pinene. This is structure of alpha pinene, and here this proton appears here. When we look at the molecule in a three-dimensional picture, this CH3 proton appear in this region. So these protons are highly shielded compared to this proton or this proton. The value of these protons are, the delta value for this is 1.63 delta, and the value of this one is 0.85 delta, and the value of this is 1.27 delta. The values here, these protons are shielded compared to these protons, but both the protons are attached to the same carbon atom. The geometry of the molecule here explains the position of the proton. It is in the shielding region of the molecule. That's why this proton is more shielded. Next we will consider for carbonyl compounds. For carbonyl compounds also consist of pi electrons. And these pi electrons are induced to circulate like this, similar to olefins, and this is the direction of applied magnetic field, and they induce secondary magnetic field. And here also two types of secondary magnetic field is obtained. One is paramagnetic field de-shielding, another one is diamagnetic shielding. So now here any protons appears, this is the paramagnetic position. These two are paramagnetic position, and this is diamagnetic position. And in the carbonyl compounds, aldehydes or ketones, the protons appears in the paramagnetic region of the molecule. So therefore all these protons are highly de-shielded. Next we will consider for example, for formyl esters. formyl esters and for aldehydes RC double bond OH. These protons, they appear in the de-shielding paramagnetic de-shielding region of the molecule. So therefore they will have a higher chemical shift values. The proton is attached to an electron withdrawing groups, and also another effect is the paramagnetic de-shielding effects, magnetic anisotropic. That is why aldehyde protons will show higher chemical shift values. And formyl esters also, here this proton also show higher chemical shift values. Next, for acetylenes. As I said earlier, acetylene protons are shielded. Acetylene protons are shielded. So acetylene, C double bond C, it consists of 2 pi electrons, 2 pi bonds. So here they are more freely induced to circulate in presence of an applied magnetic field. But in presence of an applied magnetic field, this acetylene molecule is oriented vertically on the direction of the applied magnetic field. And these pi electrons are induced to circulate in this direction, and they produce a local or a secondary magnetic field like this. For acetylene, so these positions are paramagnetic region, and this position is the diamagnetic region. And in acetylene, the protons are placed in the diamagnetic region of the molecule, and here they opposes this position. Here the pi electrons, induced magnetic field opposes the applied magnetic field. So therefore, here the resonance of these protons requires more field. That's why these protons are highly shielded or upfielded protons. That is why acetylenes will show low chemical shift values, or acetylene protons are upfielded protons. Next we will consider for aromatic compounds. For aromatic compounds, here there are 3 pi bonds or 6 pi electrons. They are delocalized and throughout the benzene ring, and they form a circular delocalization is there, and they form a secondary the electric currents. We call it as ring currents. And in presence of a ring, or by the formation of the ring currents, it forms a secondary magnetic field. This magnetic field, this is the direction of the applied magnetic field, and here it also shows 2 types of induced magnetic field. One is a diamagnetic shielding region, another one is paramagnetic de-shielding region. So here the secondary magnetic field is aligned with the applied magnetic field, and in the center of the molecule the magnetic field, secondary magnetic field opposes the applied magnetic field. So this region of the molecule we call it as a shielding region, and the periphery, this region of the molecule we call it as de-shielding region or paramagnetic region. And the protons appears all the aromatic protons, they appear in the paramagnetic region of the molecule, paramagnetic region. That is why these protons are highly de-shielded protons, or they require less magnetic field for resonance, or we call it as down-fielded protons, or they are de-shielded protons. So this is the explanation for magnetic anisotropic effects for olefinic protons, aldehydic protons, carbonyl protons, and aromatic protons and acyclic protons. So this, in the case of aromatic protons, here this region is shielded region, and here these are de-shielded. De-shielded region of the molecule. So all protons appears in the de-shielded region. That is why they are showing higher chemical shift values. So we will take an example. The magnetic anisotropy can also be explained the aromatic properties of the molecules. We will take an example. So 18 anilines. 18 anilines consists of 6 protons. They are placed in the inner side This is the compound 18 aniline. It consists of 2 types of protons. One is the peripheral protons. Peripheral protons, 18 protons are there, and in the inner 12 protons in the peripheral and 6 protons in the inner side. And these 6 protons are present in the shielding region of the molecule, and all these 12 protons, peripheral protons, in the de-shielding region of the molecule, and this chemical shift values of this is about 8.9 delta. Chemical shift value is 8.9 delta, and the inner protons chemical shift value is minus 1.8 delta. So these protons are highly shielded and peripheral protons are highly de-shielded. And we'll take another example. Toluene and the methyl groups attached to an aromatic ring and methyl group attached to a conjugated alkenes attached to an alkene. Here the delta values for the methyl group, chemical values for methyl group, it is delta is about 2.34. Chemical shift values is 2.34, and for this the chemical shift is 1.95 delta. 1.95 delta, and both the molecules, they are isomers, and here this methyl group is attached in an acyclic conjugated system, and here methyl group is attached to an aromatic conjugated system or aromatic ring. So here these protons appear or present in the deshielding or paramagnetic region of the molecule, and therefore these protons are highly deshielded and shows higher chemical shift values 2.34 delta, and here no anisotropic effects, only electronegativity, other effect is there, and here this proton appears at 1.95 delta. So this much about the magnetic anisotropy. On the basis of magnetic anisotropy, we can explain the chemical shift values of compounds containing pi bonds, olefins, aromatic protons, acyclic protons, and also aldehydes and ketones.